So we're jumping up to section 8.4, chapter 8. So Trig Sub, you're usually going to use Trig Sub for integrals involving involving the square root of a squared plus or minus u squared, or square root of u squared plus or minus a squared. And I guess the plus is the same, so u squared minus a squared. Why? Because of the Pythagorean theorem. Thank goodness for the Pythagorean theorem. This suggests sides of a right triangle. So thank goodness the Pythagorean theorem works, because that's what lets Trig Sub work. So we can turn this variable. So I'm going to say one other thing. U is some f function of x, and a is a constant. So the nice thing about this is it turns this function, this expression that involves a radical quantity into a function of an angle. And then we have some other tools to work with those angles. Now some books, you will see some books, and I'm glad that Ms. Hine teaches, that has the same philosophy that I do, that just always draw the triangle. So some books will teach, if it has this form, then make this substitution. If it has this form, make this other substitution. If it has this form, make this other substitution. You have to memorize all these substitutions. Just draw the triangle and you make the correct substitution. And when I draw my triangle, just my personal bias, I try to use sines and cosines and tangents and secants. And I would rather use sine than cosine, and I would rather use tangent than secant. So I try to draw my triangles, or I'd rather use sines and tangents than cosines and secants. That's just my personal preference. Sometimes if you don't like the trig functions that you have, you can interchange the legs of the triangles and get the cofunctions. But because I remember the derivatives and integrals of the sine and cosine and tangent better than the other ones. So that's just my personal bias. So what I want to do, I'm not going to go through a lot of examples. I think we understand this fairly well. I want to just do a couple of examples of integrals where it might not be immediately obvious that you're dealing with a trig sub. So the first one is rational powers. So this one's nice. The second one I really, really like, because it combines so many of our favorite things. So say we had, our example was to evaluate the integral of 1 over, I don't know why I put it over there so far, 1 over x squared plus 3 to the 3 halves dx. So it's not immediately obvious that this would be a trig sub. But I'm going to rewrite this as the integral of 1 over the square root of x squared plus 3 to the third. And now it looks more like the form of a trig sub. So let's set this up and do this one. So here's my triangle. Yes?
So if you have the denominator to any power over 2, you do trig sub basically?
You could do, it could be the 3/4 power.
Okay.
And then you could have a square root and a square root. So you could have a square root to the 3 halves power. Something like that. Yeah, yeah, that sounds really messy. Yeah. All right, so let's see. I set my my triangle up. So we know that this is, since this is a plus, this is our hypotenuse. And I like to put my variable on that side to get a sign. And what's this side going to be? Square root of 3. So then the cosine, I'm just going to write some relationships that we might need. Cosine is square root of 3 over the square root of x squared plus 3. Tangent x, or sorry, tangent theta. This is the one that we're going to end up using, x over the square root of 3. So that tells us that x equals square root of 3 tangent theta. So this is the one I'm going to use to get my dx. So dx is square root of 3 secant squared theta, d theta. The forgetting to substitute in for the dx is one of the easy kind of common mistakes that students make. It's easy to forget to make that substitution. So this integral becomes, so I'm going to say we don't have this square root of 3, so I'm going to say 1 over square root of 3 to the 3 halves, because we have a cosine to the third. I'm going to say that substitute a cosine to the third theta to get this third power. So I need to divide out the 3 halves. Oh, not square root of 3. 3 to the 3 halves. That's what I meant. There we go. 3 to the 3 halves. Cosine third theta, square root of 3 secant squared theta d theta. And thankfully this simplifies nicely. What does this become? 1/3? Yeah?
Can you explain again why you do the 1/3, 1 over 3 to the 3 halves out?
Because I'm saying that I have the integral of cosine to the third, but cosine to the third would be this quantity. I'm just going to write it out here. Equals root 3 over square root of x squared plus 3 to the 3 halves, or to the third. So I need to divide out that, since I don't have this here.
Why is it to the 3 halves then?
Because I have the half comes from the square root, and then I have a third. So I'm dividing that out. Because in our original integral we just have a 1. We don't have that factor, so I need to divide that out to make them the same. This 1 over 3 to the 3 halves times square root of 3 is 1/3? No? Is that yes? Yeah? Cosine to the third times secant squared is cosine theta?
Sounds good.
Is this good? Are we good here?
Why did we?
What?
What happened to those two
Wait,
squares?
27 counted.
3 halves.
That wrong.
This 3 halves?
Yeah, because I realized that you factored out the other and that one. But wouldn't that only get rid of one of them? Because there's 3 of them.
So should it be 1/3? Should it be 3 to the third? Yeah?
Because it's 3 to the 1/2.
Right.
You're multiplying by that. So it's 3 to the 1/2 and 3 to the 3.
3 halves. So 1/2 minus 3 halves is,
-1. So it's still 1/3.
yeah, so it's just 1/3, right?
Okay, just 1/3. Got it.
1/2 minus 3 halves. Yeah? Are we good?
Yeah, we're
Okay. All right. We have 3 to the 1/2 over 3 to the 3 halves. So 1/2 minus 3/2 is just minus 1. 3 to the minus 1. Okay. All right. I just want to make sure we agreed on our arithmetic. And this is an easy integral. 1/3 sine theta plus c. And we also need to back substitute. So from the triangle, sine theta is x over square root of x squared plus 3. So this equals x over 3 square root x squared plus 3 plus c. All right. So rational powers, another opportunity or another place where you can use trig sub. Let's look at one more. This one I think we'll really like.
I don't like
How about this one? This one kind of looks a little bit messy, doesn't it?
Yeah. That's why we skip. That's what this.
Bottom page of that side.
No,
13th prime.
So what are we gonna do here?
We solve by skipping.
Huh?
Solved by x squared plus 4x plus 4 plus 9.
So in other words, what complete the square?
I give up.
It's awesome when we get to complete the square.
No, it's not.
All right. So this is equal to the integral of dx over the square root of x squared. What is? How did we do it, Ethan?
My head. You divide by 2 or something. Divide by 2 or something.
So I'm going to say, so plus 4, I'm going to do it in one more step. So we're going to do x squared plus 4x. We divide this by 2 and square it. Plus 4, but we don't want to change anything. So I'm going to, and that's what I'm going to, that's my perfect square. So I do a minus 4 plus 13. So I just added one more step to what you said. So this is how I completed the square by adding 4 here, but I need to subtract 4 so I don't really change it. So this becomes the integral of dx over the square root of x plus 2 quantity squared plus 9. And this is a trig sub. And one of the sides of the triangle, instead of just x, is going to be x plus 2. Isn't that nice?
Is it a rule, like it should be a rule that you always have to make your triangle that way instead of the other way?
I don't know if it's a rule, but I always do. I don't know.
Okay.
I don't know
So
why.
it's a rule.
Does anybody like to draw their triangle the other way?
I draw it upside down.
You draw it like you draw it like this? You draw it that way?
Well, I mean, if it's in the first one.
And then this side, this is our hypotenuse. This is our quantity here. All right, so we have this quantity in the denominator. So I'm going to say the substitution I'm going to make is cosine theta equals 3 over
That big one.
the square root of this thing. And tangent theta is x plus 2 over 3. So this gives us our relationship for x. X equals 3 tangent theta minus 2. So dx is 3 secant squared theta d theta. And now I'm going to substitute. The integral, I don't have this 3 in my original integral, so we get a 1/3, and I get a cosine theta. That gets me this quantity in the denominator there. And then I have my d theta. I'm going to write that 3 secant squared theta d theta. And this just gets this the integral of secant theta d theta. No, the 3 and the 1/3 cancel. This is in the numerator. Do we remember what this integral is? Secant theta plus tangent theta plus c. And now we need to substitute. So secant theta is the reciprocal of this. And I'm going to write it in its original form. And tangent theta is x plus 2 over 3. And we get it plus c. So you can complete the square and do trig sub as well when you have a square root of a, I'll scroll back down in just a second, of a polynomial, or a quadratic polynomial. So a couple of situations where you can use trig sub that may not be as familiar as others. All right, are we good? Okay, homework, and I have a couple of hints on your homework. Now, I'm going to say this is, there are a lot of problems here, a lot of trig sub problems. Every other fifth, every other even odd. Oh, a page.
Wait, we don't have to do all these?
Just do the, I would say just do the hardest ones because they're the most fun.
How many can you do?
Oh, keep going, coach.
So how many should we do though?
You could skip one or two.
One or two.
So we could do one or two? So we skip all the ones with ones or twos.
So wait, where's that?
That's what
Number 41 is integration by parts plus trig sub. I would suggest doing that one because it's fun. For number 51, integration by parts. Number 51, you end up with a secant to the third theta. You do that by integration by parts.
We didn't decide 51.
I didn't assign 51. Did I miss it?
Add it on there.
No.
Let me double check. It might be, that might be the number from the previous, the old textbook. And number 72, I'm going to say is difficult.
Oh, thank you.
For that one you do trig sub on a portion of the integrand, not the entire thing. And let me check that number there, and I'm going to stop this because we don't need the comments. Whoops.